Good afternoon, everybody. This is a live severe weather briefing on the conditional tornado threat that looks like it could come together this evening across southeastern Saskatchewan. Canada has definitely been a hot spot so far during this quiet 2020 season for tornadoes, especially in the central and southern plains in the U.S. Up in Canada, there's been some incredibly photogenic tornadoes. There was one in southern Saskatchewan that was also an east-southeasterly mover that produced a pretty substantial tornado. That was intercepted by the veteran storm chaser Craig Hilt up there in southern Saskatchewan. Then just about a week ago, a few days ago, less than a week, there was an incredible supercell in southwestern Manitoba. We broke down the meteorological setup for that tornado, as well as some storm structure. And it looks like there could be another conditional tornado threat this evening, late afternoon and evening across southeastern Saskatchewan. The conditional part of that depends on how much SIN, or convective inhibition, which is the opposite of CAPE. It's negative buoyancy, stable air, and some of the models are indicating quite a bit of SIN in the low levels of the atmosphere. And if that happens, that'll mean that these storms will have a struggle to become surface-based. However, if some surface-based supercells do develop, then there is ample low-level wind shear for a tornado threat. The parameters look pretty substantial out here across southeastern Saskatchewan, but you always want to dig a little bit deeper into those parameters and try to see if there are any negative factors as well for tornadoes. And I was looking at some of the soundings, some of the other parameters like SIN, or convective inhibition, at the low levels, and that's really the thing that could cause this setup to underperform a little bit, even though those parameters are suggesting even a threat of a strong tornado if those storms can go surface-based. I'm just not entirely sure that that's going to happen. But here's the upper level storm system that is responsible for all of this. And I just showed you that the target area. I'm going to keep that one pulled up just a bit here, and now the 500 millibar map. And there's a vortex that is centered over northern Alberta, and a belt of stronger westerly mid and upper level flow extends on the southern and the southeastern flank of that upper level storm system. That stronger belt of flow passes over Idaho, through Montana, and up into southern and central Saskatchewan, and right on the southeastern periphery of that stronger upper level flow. That's where the target area is located for today. Plenty of bulk shear, plenty of low-level shear as well. And in fact, on a synoptic scale sense, this setup actually looks more favorable than the last couple Canadian setups, and that's because the mid and upper level flow, the trough, is pretty coupled with the low-level jet, a large-scale low-level jet as well, that I'll show you here in a second. Let's just head on down to 850 millibars. And look at how that strong mid and upper level flow and the cyclonic curvature to that flow is co-located with a robust low-level jet. And the low-level jet is that channel of wind about 1 kilometer above the ground out of the due south that usually fires out ahead of a large-scale cyclonic trough like we're seeing right now at the mid-levels. And this belt right here of strong 1 to 2 kilometer flow, that's the low-level jet that's developing ahead of this upper level storm system, and that's because of the pressure gradient with lower pressure to the west, also driven by the elevation increase, the general elevation increase from east to west. That helps to maintain that pressure gradient with the low pressure to the west, higher pressure off to the east, and that squeeze play at 1 to 2 kilometers just above the ground leads to a southerly low-level jet, and these low-level jets are crucial to generate the low-level shear necessary for tornadoes. And you can see a little bit of an enhancement in the low-level jet down here across the target area, and that's part of a large-scale, synoptic scale low-level jet. So overall, on the larger scale, this setup actually looks more favorable than the other Canadian setups that we looked at. Oftentimes in Canada, when you get a powerful upper-level storm system like this, you'll see that the low-level jet will be shunted way off to the southeast, and that's why those outflow boundaries, or MCVs, often generate more tornadoes on the U.S. side than they do in Canada. But every now and then, the low levels and the upper levels of the strong storm systems during the late season are coupled like this one, and that can lead to some pretty substantial tornadoes across Canada. That's what happened on the Tilston Day back in 2015 with a very large tornado. But this one is a bit more marginal. in terms of the thermodynamics and the low-level convective inhibition, as we're going to analyze here shortly. So even though this looks very favorable initially on paper in terms of the upper levels and the parameter space, the composite parameters, when you dig a little bit deeper, you realize that there is quite a bit of convective inhibition with these storms. So here are the NAM forecast 0 to 3 kilometer energy helicity index, and this is one of the most commonly used composite indices to forecast, and this is based on surface-based CAPE and storm relative helicity in the lowest 3 kilometers. Usually these 3 kilometer indices are a more accurate representation of the wind shear in the high plains and the northern plains, and that includes the Canadian prairies. And here the NAM is forecasting a blob of EHI, which is a combination of that CAPE instability and also low-level wind shear. And but I clicked on a forecast sounding pretty close to that maximum in EHI, and those maxima are co-located with maxima in the convective inhibition, or maxima in the low-level stability, the opposite of instability, the opposite of CAPE, basically negative CAPE. That's what SIN is. So if you're taking a hot air balloon, a real infinitesimal hot air balloon that's the size of an air parcel, that's parcel theory, and you rise up into that stable air, suddenly the surrounding environment's going to be warmer than that hot air balloon, and the hot air balloon is going to want to sink back down. The opposite is true with CAPE, whereas if you have those steep lapse rates or cooling temperatures with height, that hot air balloon, which is going to want to maintain the same temperature as it lifts up into the atmosphere, if those temperatures surrounding it cool rapidly with height, then suddenly that hot air balloon is going to find itself in an environment where it's warmer than the surrounding temperatures, and it's going to rise. And those are the fundamentals with CAPE. It's the opposite of SIN. But if you do look at some forecast soundings within these blobs of high parameters, you might look at this and you think, wow, there's going to be a tornado outbreak across southeastern Saskatchewan. But then you look a little bit deeper, the forecast sounding, and first of all, I'll show you this map of SIN, whereas the bright colors in this case are stronger convective stability, the opposite of CAPE. And this is the same model that I just showed you that showed that pretty strong area there of EHI and 0 to 3 kilometer storm relative helicity. This right here shows that there is some non-zero SIN. So the white coloring is a complete lack of stability or convective inhibition, and these little blue areas in yellow, that's negative buoyancy. So the balloon, the hot air balloon that's rising from the surface, is going to rise into air that's actually warmer than it, and it's going to cause it to want to sink back to the ground. And there's a couple things that can cause a storm to overcome this convective inhibition and become surface-based. The NAM model actually shows the least amount of SIN over the target area across southeastern Saskatchewan. That's on the order of about 10 to 20 joules per kilogram. That minimal SIN, or low-level stability, can pretty easily be overcome by a supercell that has an intense mesocyclone that strengthens. It's able to drill down through that layer. Sometimes a front or a dry line can punch into this environment. You can see some low-level, a lack of low-level stability there in south central Saskatchewan, a little bit further west. Storms could develop there initially, become surface-based, and then develop stout low-level mesocyclones. And those storms are actually capable of moving into an environment with strong SIN and still surviving. Many of the strong tornadoes that we've seen actually do happen in environments with a lot of low-level stable air. And in fact, the one about 5 days ago in southwestern Manitoba, that was in an environment of low-level SIN. The Greensburg, Kansas tornado, for example, famously happened in an environment of 80 to 100 joules per kilogram SIN. But those storms already generated strong low-level mesocyclones earlier in the day when there was less convective inhibition, and then they just continued to survive overnight with that strong low-level mesocyclone drilling through that stable air. But the NAM model actually has the least amount of SIN compared to the other models. But I'll show you first what that SIN looks like in the forecast sounding from the same area. And this is from the NAM model as well. And then I'm going to show you the RAP model and the HRRR convective inhibition. Compare those and then compare their convective scenarios and how it unfolds. But this right here is that convective inhibition that's being analyzed by the models. This is in the forecast sounding. You can see a lot of positive CAPE in the mid and high levels because of those steep lapse rates, or how rapidly those temperatures are cooling with height. That's all positive CAPE right there. But you've got negative CAPE down here. This is the opposite. This is SIN, or convective inhibition. So if you're taking a balloon with those temperature and dew point characteristics at the surface, those are conserved as that balloon lifts up through the atmosphere. That balloon is the size of a very tiny parcel of air. And as that lifts up, notice how the red line is actually warmer than it. And that's going to encourage the balloon to go back down. That's, in a very basic sense, that's atmospheric stability right there. But if that balloon is able to punch through that capping inversion and then emerge into this area of positive CAPE, then notice how the temperature of that balloon is actually warmer than the surrounding air. It's warmer than the red line, so that balloon continues to rise until it reaches the top of the atmosphere. That's basically the tropopause, the top of the lower troposphere. And at that time, the temperature of the balloon becomes equal with the surrounding environment. And if it wants to try to rise into the stratosphere, notice how the temperature increases, and as the environmental temperature is warmer than that balloon, and then it's going to want to sink back down. Sometimes the updraft can be so intense it can punch above that equilibrium layer, as we call it, and that is what is called an overshooting top with severe storms that you can see visually from a distance. You can see those storms, you can see the flat anvil, and a little bubble is an overshooting top, and that's an inertial acceleration because the updraft is so intense. Those parcels actually poke through that equilibrium layer and can surge into the stratosphere before falling back down again. But those storms that have an overshooting top, those are the most intense updrafts, the more severe storms, capable of producing even more impactful severe weather at the surface. But look at this wind profile here. You see changing wind direction with height. You see a lot of speed shear, a strong low-level jet in excess of 50 knots. That's a profile that would be capable of a strong tornado if it was based at the surface and you didn't have that low-level SIN. But because of that convective inhibition and this capping inversion, that actually acts to increase the low-level wind shear because it causes the low-level winds to be more easterly and a little bit weaker. It causes the low-level jet to be a little bit stronger. And so that's why with those big blobs of composite parameters that show a strong tornado and a big-time photograph like this, if you dig a little bit further, dig a little deeper, you can see that sometimes those are correlated with insurmountable SIN, or a capping inversion that is too strong to allow for surface-based storms and to allow those storms to really take advantage of this incredible wind shear. And a lot of easterlies at low levels. This is the 1 kilometer wind, south-southeast at 40 knots. Pretty strong mid and upper level winds as well. You can see quite a bit of vertical motion here in the sounding at the same level as that capping inversion. That tells me that there's a likelihood of elevated supercells, at least on the northern side of that instability axis. So with that vertical motion, that should aid storms to punch through that capping inversion, or that SIN, that warm front, and you're probably going to get quite a bit of severe storms and updrafts that are able to take advantage of that SIN above. But this sounding is a little bit inflated, a little bit of an over-representation of how favorable the environment is for tornadoes, and that's because of that low-level convective inhibition. The NAM, which has the least of which of that low-level SIN. Here is the RAT model, and this is from the pivotalweather.com website, an incredible website for visualizing this model data. This is the surface-based SIN. The brighter colors, the brighter reds, that's greater stability or greater negative buoyancy, and quite a bit of SIN depicted by the RAP across southeastern Saskatchewan, more so than even the NAM model. And usually the RAP model is my model of choice when I'm forecasting for the high plains or the Canadian prairies, thermodynamics, where the convection might happen. But even so, with this area of general SIN, you can see this little stripe there in the whitish color where there's a minimum of convective inhibition, and that's where the RAP fires storms in extreme south-central Saskatchewan, out ahead of that surging Pacific front, that area of minimal SIN there. And time will tell whether those storms can quickly develop strong low-level mesocyclones that are capable of surviving moving into that prime environment in southeastern Saskatchewan kinematically, or in terms of its wind shear. but is characterized by a lot of low-level stability, as we saw in that forecast sounding from the NAM. But the RAP has even more convective inhibition than the SIN and still fires storms down there. This is a powerful upper-level system, a lot of cyclonic curvature to the upper-level flow, a lot of upward motion ahead of this system. There's a pretty strong surging front that's going to generate a lot of low-level convergence and upward motion in the vicinity of that SIN, which should help at least elevated supercells to form. And with that magnitude of wind shear, there's a decent chance that those elevated supercells could develop low-level mesocyclones that are strong enough to drill through that stable layer. Looking at the HRRR, this is a bit of a zoomed-in visualization of that low-level stability. And even the HRRR, which often overmixes the dew points and shows almost no SIN because the environment's often so well mixed up here in the northern plains and northern high plains. Here is that surging Pacific front with a lot of SIN back behind, as that's that frontal inversion that's pushing east. A lot of convergence along this frontal boundary as well. And the NAM is definitely showing a little bit less SIN up near where Sean Schofer lives, up near Melville, up to Yorkton, up along that Manitoba border. That's what the HRRR is showing, so there's a chance that there could be a couple renegade monsters up here just to the west of Sean's place that maybe will form on the apex of this bulging Pacific front and will move through this environment right here. That environment's a nice corridor where a low-level mesocyclone can develop and continue to move northeast through that corridor. There's a pretty stout pipe of minimal convective inhibition there at the low levels, where I think that there is a chance that a storm could materialize. So now let's look at the individual models. We'll pull up the internet here and see what the models are showing in terms of the convective evolution later on this afternoon. Most of the models show storms developing along that bulging Pacific front in south central Saskatchewan by about 5 to 6 o'clock and maturing thereafter. So here's what the HRRR is showing. And the HRRR is in pretty close agreement with the RAP model. This is at 23Z, which is about 6 p.m. Central Time. And this is also on the Pivotal Weather website. And it shows surface-based storms developing in the far northwestern corner of North Dakota into far southeastern Saskatchewan. A relative lack of storms developing in that SIN hole that we were just analyzing, or that hole in the convective inhibition. And now here at 0Z, which is 7 p.m. Central Time, it's starting to show an intensification of that storm, moving right into that corridor of reduced SIN. But the HRRR is showing largely transient supercell structures, storms developing along that front and having difficulty moving in to the open warm sector because of that convective inhibition. They seem to have a bit of a quasi-linear configuration with storms getting forced up by that Pacific front off to the west. But there's a chance if any of these storms can become long-lived, strong low-level mesocyclones and can move into this environment of a greater SIN out ahead of it, well, the HRRR actually is doing what it always does and over-mixing out those dew points. So we probably should throw out the HRRR. It actually mixes out dew points ahead of those storms down into the mid-50s with 30-degree dew point spreads, inverted V soundings, a reduction of wind shear. It's possible that could be correct. Let's look at the 3-kilometer NAM really quick. 3-kilometer NAM shows more of a linear configuration. Too much SIN out ahead of that Pacific front. And in fact, the 3-kilometer NAM mixes dew points down into the upper 50s, which is still tough. Look at that cloud layer that it has too at the mid-levels of the atmosphere. Probably some kind of a cirrus shield or even anvil blow-off, orphan anvils from storms that are trying to develop on the front but don't make it into that stable air. So wow. Based on these models, it sure is looking to me like convective inhibition may just be too much. The RAP model here, though, initiates a convective line to the north of Yorkton. It's possible up near the nose of that instability axis there could be more pooled moisture, a little bit less mixing up there. But it's looking like a a convective line forced by a surging Pacific front is going to be the dominant mode. It's a little bit drier up there in southeastern Saskatchewan. Still, though, the wrap does pool dew points into the upper 60s along that warm front up near Yorkton. And it does still have more of a marginal tornado setup. So I would suggest targeting up near the Yorkton area on this day. I know my target area largely has southeastern Saskatchewan, but it's a conditional tornado threat. This moisture, the wrap looks like it's behind the front. Looks like that's not behind the front, so that's ahead of that Pacific front. There is a little bit of pooling of those dew points too. So the wrap seems to mix out those dew points the least, but look at all that sin across southeastern Saskatchewan right now. It's about the midday hour out there, closing in on 1 p.m. It does look like some erosion of that convective inhibition off to the deeper into the instability axis. Stepping forward with time, and this is basically the wrap model, the Storm Prediction Center mesoanalysis, and it does have a bit of an erosion of sin right near the intersection of the northwest corner of North Dakota and Saskatchewan, just ahead of that bulging Pacific front, and that's where the wrap has the greatest likelihood of surface-based storms, or up near Yorkton along the warm front to the north of Melville. There is a chance there could be some pooling of dew points up there as well, but probably a mega shelf that's going to form along this surging Pacific front in far southern Saskatchewan. Probably a pretty substantial wind threat as well down there. But a lot of wind shear, so it's a conditional tornado threat, because if dew points verify a little bit higher, if the mesocyclones are strong enough to push into that convective inhibition, then there certainly is a chance of tornadoes throughout this convective line. But I think that the two areas to target are either pretty close to the North Dakota border or up near Yorkton. I do think there's a threat of tornadoes tomorrow out in northwestern Minnesota. This is at 0Z. Tons of big-time dew points across northwestern Minnesota and along the Red River Valley up there of eastern North Dakota. So that's what I've got my eye on in terms of chasing. I may do a last-second deployment up there to the Red River Valley, eastern North Dakota, Fargo, Grand Forks, into northwestern Minnesota. That's the area that I really like tomorrow. The wrap model flattens out this upper level system, flattens out the ridge just a little bit, bringing that stronger westerly flow, mid-level westerlies, bringing the jet stream back into the northern U.S., which could activate the high plains of Colorado and Wyoming as well. But northwestern Minnesota then gets a taste of that fringe of the stronger flow, some cyclonic curvature up there. Pretty stout low-level jet into northwestern Minnesota as well. That's the 1 kilometer wind. You've got a 30 to 40 knot low-level jet there. A little bit east of the Red River Valley. Notice that. Looking at the 0 to 1 energy calicity index, looks maximized there. Just to the east of Fargo, that hot spot across central and northern Minnesota that has been getting so many tornadoes so far this year. It looks like that area could be under the gun again tomorrow. Not the most incredible looking photograph, but these often produce incredible tornadoes across central and northern Minnesota and the Corn Belt. Big time moisture, as is often the case this time of year, up there in the northern part of the Corn Belt, the lake region of northern Minnesota. Low 70 to mid 70s dew points. A little bit of backing wind also. There's probably going to be an outflow boundary in this environment. So tomorrow looks quite interesting up there in western Minnesota. We'll have to keep a very close eye on that. Just for fun, we can look at the supercell composite closing in on 20 up there. Right in that hot spot too, that west central, northwestern Minnesota area, Otter Tail County. Even though this photograph looks a little bit straight line, we'll probably have a little stronger of a low level jet. I selected a forecast sounding too that's a little bit west of that low level jet axis, so you probably got southerly winds that are a little bit stronger, 30 to 40 knots up there further east. So a storm that can develop in this environment and then move a little further east into the core of that low level jet could certainly develop a tornado threat. This one actually looks pretty similar to the Dalton, Minnesota setup. So see, as I've gone just a little bit further east, notice how that 1 kilometer wind is more backed and stronger, more favorable hodograph shape. So we're going to be monitoring tomorrow really closely during our live briefing. And I do think that central and northern Minnesota could be quite active tomorrow. And of course, we're watching the tropics. The Atlantic, we got a tropical depression that is forecast to become Tropical Storm Josephine. The long-range models, though, are showing that storm to recurve and become a fish storm. The eastern tropical Pacific is incredibly active, and many of the models have shown a hurricane even threatening Cabo San Lucas next week. Keeping a close eye on that. Might make a last-second deployment to Mexico to intercept that. Working closely with Don at Radar Omega to have a network of live streaming cameras and pressure sensors ahead of the hurricane. Working with Mike on the Windy Palms project. Working with Mark, Chase and Spin on the subsonic sensors. So we've got a lot of exciting science planned ahead. Just for fun, really quick, let's look at the SIG tornado parameter. And there you can see it maximized across western, northwestern Minnesota. That's according to the RAP. Looking at the NAM model, probably has it up there. NAM not quite as aggressive as the RAP in that tornado potential, but it also has the northwestern corner of Minnesota, hinting at least a pretty substantial tornado and supercell threat up there. And this is just the regular NAM model. Looking at the 3 kilometer NAM up there, also a bit of that, but kind of a weird looking setup. But those are the ones that go big in northern Minnesota. And we'll look at that later on tonight or tomorrow morning. And I'll definitely let you guys know if I decide to do a deployment out there. I do think there's an opportunity, RJ, to chase into Manitoba for the Canadian chasers up there. I know that if you do cross provincial lines, I think you might have to quarantine. I don't think I'm even allowed to go up there. Pretty sure that I'm not allowed to go up there, but I really wish I could chase Canada. But the big tornado in Canada was probably missed. That was definitely about 4 or 5 days ago there in southwestern Manitoba. Let's read in some of these questions here. Pull up the target area again, just so you guys you can already see your questions. And I am going to be building the studio here as well. So I'm going to put it in the corner of this room. So that way I can put little posters up, all kinds of things. So I'm thinking that the corner of the room will probably work better. Than I could put a tornado photo on one side, a tornado photo on the other side. And then I'm going to really start to dig deep into the educational material too. We just scratched the surface on CAPE and SIN in this discussion, but I can break it down and do some graphics and get a blank piece of paper and show you some of the mathematics of that as well. Basically, all meteorology is you take mathematics as almost another language to describe what we're seeing happening in the atmosphere. So when I kind of describe the physical side of these, or what's actually happening in the atmosphere, really all math is confirms the concept of stability, the concept of parcel theory, the concept that a mesocyclone actually enhances the upward motion in the updraft of a supercell. The rotation enhances that. Even how much the flow responds to the Earth's rotation, you can mathematically prove that. There's a thing called the Rossby radius of deformation, whereas weather phenomena that are on a scale larger than that, Coriolis force is considered important, and those weather phenomena that are smaller than that scale, like tornadoes or on the storm scale, Coriolis force has very minimal importance for those flows that are on the smaller space and time scales. Yeah, the smoke is crazy here in Colorado too, and I know it's making it up there in the high plains. I definitely wake up with a bit of a dry throat and some allergies these days because of all that smoke that's happening. I know that the Grizzly Creek fire is still going out there near I-70. This morning, visually, the smoke looks a little bit less up there, so I'm hoping that that means that that fire is getting more contained. Yesterday, I saw the community of No Name was getting evacuated. I know there's a lot of campers and A lot of summer activities that happen out there. But the community of No Name was getting evacuated as that Grizzly Creek fire continued to expand. If I saw that happening, I probably would have gone out there a couple days ago to see that storm as it initiates, but now I just feel like I'd be getting in the way if I went out there to western Colorado. We're just keeping a close eye on hurricane season there in the tropical Atlantic and the Pacific to intercept. So thank you everybody for joining me for this 30-minute weather briefing, where we also like to educate a little bit on severe weather. Good luck to all the Canadian chasers up there that will be chasing this target area. That target area, I did arc further north. I just have a feeling that because the convective inhibition is so substantial that there could be something up here near Saskatoon that goes big. Some type of a fluke tornado up there, far north up to the northern side or the nose of the instability axis, where you can get a little bit more moisture pooling. So if you really wanted to take a gamble up there as a Canadian chaser, I'd maybe head up towards Saskatoon or just to the southeast of Saskatoon and see what happens there with a little bit more pooled moisture, less convective inhibition, and kind of closer to the core of that low-level jet. Or you could work down here closer to the North Dakota border, where it looks like the NAM has a bit of a wedge of surface-based instability that noses into far southern and southeastern Saskatchewan. But if I was up there, I'd probably try to convince Sean to head northwest out of Melville, up a little bit closer to Saskatoon, and I wouldn't be surprised if there's a pretty big tornado up that far north. So thank you everybody, and have a good rest of your Wednesday, and we'll see what happens. These conditional target areas are sometimes interesting to watch play out. I think what's going to happen is those storms are going to be elevated above stable air and forced up by that front, but there is a couple different scenarios that could lead to tornado potential. So thanks everybody, and have a good rest of your day. Never stop chasing.